This video focuses on how to parameterize the momentum 4 vector for massless particles such as photons. It then makes use of the null nature of these vectors to describe the motion of these particles along principal null geodesics in the equatorial plane of the Kerr geometry. Basically, how does light and other massless particles move around an uncharged rotating black hole, or in the vicinity of an uncharged rotating black hole? Right, so we want to describe the motion of massless particles such as photons, gravitons, and perhaps some neutrinos in the equatorial plane of a rotating uncharged black hole. Now, these particles travel along geodesics described using the coordinates x, mu. There being 4 coordinates. We can parameterize the world line of these particles in the form x mu is u mu lambda, and lambda is a parameter, and u mu I'll get to shortly. All right. Now, we can't parameterize the path of these particles using proper time since d tau is 0 between any two events on the world line of the photon or other particle. But there are other parameters we can use. Now, in some arbitrary inertial frame, let's have a look at an example of one. For instance, what are we talking about? In some arbitrary inertial frame, we can describe the path of a light ray traveling along the x-axis to be x equals ct, and a space-time diagram plot here. Y and z directions suppressed. Now, the world line of this light ray is described by its coordinates x mu is ct, x, y, z in Minkowski space. And first component ct, second component x equals ct, so ct goes here as well, 0, 0, because no motion in the y or z directions. Now, where the parameter we are using here is lambda equals ct. Now, we can write this parametrically in the form x mu equals u mu lambda, where u mu are the components of a vector 1, 1, 0, 0. All right. So this is a constant vector. And x, the derivative of these with respect to the parameter lambda, x dot meaning dx mu d lambda, is u mu. Okay, so the derivative of this with respect to lambda, the parameter lambda, is just u mu. All right, now the tangent vector to this world line is the vector u equals x dot u e mu, writing it in the basis, expanding it in the basis vectors, e mu, or u mu, e mu. All right, so we have our rotating mass here. Here's our light ray here, traveling here, and we're going to be talking only about the equatorial plane. And this 4 vector, if you like, 4 velocity of the particle is this. Here's the tangent vector. The 4 vector is this vector here, tangent to the path at each point along the path. Now, vectors exist in the tangent space at each point of the space-time manifold, and that tangent space is locally Minkowski space-time, locally that is. So the laws of special relativity apply at each and every point. There's a separate, unique tangent space at each and every point on the space-time manifold, wherever the geodesics are that we're talking about. So these vectors exist in a tangent space, and at that point, and for a small region around that point, the laws of special relativity apply for a small enough region of space-time around that point. These diagrams are visual aid. I can't show their time axis, obviously, so you just have to imagine it. All right, now this is a null vector, this 4 vector u, and we can use the Minkowski flat space metric eta mu nu to contract that, and so that we can find the magnitude squared of this vector. And when we do that, we put these in here, u mu, u nu, and we expand it out. There's only 2 components for the u vector, the time component and the first spatial component. When we do that, we get -1 times 1 times 1 plus +1 times +1 times +1. I've just chosen to write that as -1 times 1 plus 1 times 1 adds to 0. So we can see that's a null vector. The tangent to the world line there is a null vector. So the world line is a null curve, and because a null curve will have as its tangent a null vector. And the equation of motion of the photons given by du d lambda is 0. You can see that u is a constant vector. If we differentiate with respect to lambda, the total derivative, it's 0. Now, this is a vector equation, and since vectors are tensors, we then know that this equation holds true in all coordinate systems. Okay, what can we do with this vector u? So any scalar multiple of this vector, alpha times u, is alpha x dot u e mu, expanding in terms of basis vector, is also a null vector because we're just taking the vector u, multiplying it by a scalar. And as I showed in the previous video, scalar times u dotted with scalar times u, this will work out to be 0 as well, simply because u dot u is 0. And 0 times a scalar squared is 0. I've shown all that in the last video. Now we are free to rescale coordinates as necessary. So take, for example, the coordinate x mu and multiply by some scale factor alpha to produce a new coordinate x bar of mu is alpha x mu. Now we still have the same coordinate, but just rescaled. And having rescaled it, we don't necessarily need to continue to retain the bar at the top. We can simply just call it x mu again. Okay, but just be aware on the understanding, of course, that it's rescaled from a previous x mu. Now we can still differentiate this radial coordinate in the usual way. Dx bar mu d lambda is alpha times dx mu d lambda. Doesn't change. We can describe the motion of a photon using its form momentum vector. P is x dot mu e mu. Okay, because what we're going to do is we're going to rescale the x mu and its derivative as well, so that we can parameterize the momentum 4 vector for a photon or other massless particle in terms of the derivatives of its coordinates. So where the components are scaled such that the components of P, the vector P mu is x dot 0, x1 dot, x2 dot, x3 dot, is E on C, P1, P2, P3, okay, the usual components. So we have to scale this in this fashion up here, such that we can use the derivatives of those coordinates to represent the components of the form momentum vector for a photon or other massless particle. Okay, the form momentum vector of the photon is tangent to its world line. Okay, so here's our form momentum vector. Okay, expand in terms of the basis vectors, multiply each of the relevant components, the derivatives of each of the coordinates. P mu components are x dot 0, blah, blah, blah. And in this particular case, we're going to use the Boyer-Lindquist coordinates, CTR, theta, and phi dot, and the derivatives of those. Again, just imagine the time axis. Okay, so our momentum vector is tangent to the world line of the particle, tangent to the geodesic that the photon follows. It lives in a tangent space at each point. So at this point here, where the cursor is pointing, that's a tangent space to that point there, and the vector, the momentum 4 vector, lives in that Minkowski space at that point. And there'll be a different Minkowski space at a different point. Okay. All right, now photons travel along null curves, and the tangent to a null curve is a null vector. A null vector has 0 magnitude, so the magnitude squared is 0, or okay, which means that the form momentum vector of a photon of base P dot P is 0. Its magnitude is actually the square root of that, of course, but here I'm just using magnitude squared. The square root of 0 is still 0, so I dispense with the square root sign and just talk about the magnitude squared. Now, in component form, if we want to perform this contraction in the Kerr space-time or whatever space-time we're dealing with, then we need to go from the space Minkowski metric over to the curved space metric, d mu nu. Okay, so the magnitude of this vector in any space with metric g mu nu will be g mu nu p nu. Contracting that, we have p mu up and p mu down. Okay, these one component up, one component down, we sum them out to give us a scalar. We can write that another way as the inverse metric g mu nu and the covariant components of the momentum 4 vector p nu. But either way, when we contract, this magnitude squared must be 0. It's a null vector. In the equatorial plane, we have theta as pi on 2, and because we're restricting motion to the equatorial plane, the theta polar angle component of momentum is 0. All right, and so the above equation becomes this. If we expand this last one out here, we get GTT PT squared plus 2 GT phi PT P phi plus GRR and so on You get the idea. The one that's missing is the theta component because we've set that to 0. Okay, now just some notation things. X dot mu, just remind you, is dx mu d lambda. R dot means dr d lambda. The covariant component in the radial direction of the form momentum. That component is the metric term gr times the contravariant component r dot. The theta d lambda equals theta dot is 0 and theta is pi on 2. So just making clear there. All right, now, so on the previous slide, they had PR, P subscript R, the covariant component, and P theta are both 0 anyway. There's only two others to find. That's the time component momentum and the phi component, and we want the covariant versions of those. That's the index lowered. So PT is this. We use the metric to lower the contravariant components, x dot 0 and G03 x dot 3. That's the same as GTT, CT dot plus GT phi dot. And from previous video, we found that was minus E on C because that's the time component of the momentum lowered, so hence the minus sign there. But we also found in the last video, the one just before this, that this E on C was equal to C times epsilon, the energy parameter epsilon. And okay, we found actually that E on C squared was equal to epsilon, and that then told us that E over C is C times epsilon. Okay, obviously we had the minus that's been pointed out in previous videos because these terms are negative and negative. We can't have negative energy, so we have to put the negative term there. The phi component momentum, that's the angular momentum around the rotation axis. That, expanding that out, G30 x dot 0, zeros contract to leave us with the 3 term, which is phi, the third component, phi. Remember, 0 component was time, first component was r, second component was theta, third component was phi. So g phi t ct dot plus g phi phi dot is equal to a constant h, which is the angular momentum. Okay, this gives us two equations. We can solve this system of simultaneous equations because we want to get each of the component derivatives separate. So we want ct dot in terms of some expression here and phi dot in terms of some expression here. So we can just use matrix alphabet to do that, which is what's done here. Take these into here, call them that. I'm just giving them these names A11, A12 in order to just point out what the determinant is. Just explain what I'm doing. This is matrix M. It's equal to minus C epsilon on H for the right-hand side of these equations. And what we need to do in order to get these components, CT dot, phi dot, is we need to multiply the right-hand components, what the equations equal, by the inverse matrix. Now, the determinant of matrix M is this. And when we work that out in a previous video, I think the very first video in this series, we covered that. And I've explained what all that is and shown how that comes about, although you can see it just from here. A11, so that times that minus that times that. Okay, keep going. Okay, now the inverse, M inverse is 1 on the determinant times the adjoint to the matrix. The adjoint just came from swapping these two and putting negatives on these two. When we do that, put that in, we get this, and the solution then is ct dot phi dot is M inverse minus C epsilon H is this object here. And when we multiply that out, ct dot gives us this object, and phi dot gives us this object here. Okay, now from the very first video in this series, we showed that this, I'm pretty sure it's the very first video in this series, showed that this object here is minus delta sine squared theta, where delta is a squared plus r squared minus 2gm r on c squared. Remember that becomes singular at the event horizon. Now, 1 on this is minus 1 on delta sine squared theta. So our first coordinate has the form ct dot as this, and when we substitute in the metric terms, expand everything out, that sine squared theta is going to cancel out with these two here. We're left with this object here. Okay, I haven't yet got down to the equatorial plane. I'm coming to that. And our second, because the equatorial plane theta is pi on 2, sine theta becomes 1, cos theta is 0. Our second component, the phi dot component, phi dot was this object here. Substituting in the metric terms, we have this, gives us all this. Okay, now what we wanted to do is, remember right from the beginning, we're concerned with the equatorial plane and motion in the equatorial plane. Okay, so we're going to set theta as pi on 2. So when we go back over our previous two coordinates, we get ct dot. Well, for instance, if you look at this last one, phi dot here, sine theta of pi on 2, or sine of pi on 2, sorry, is 1, and 1 squared is 1. So that disappears. Cos of pi on 2 is 0, so that disappears there. And what we end up with, ct dot is 1 on delta, all of this. Phi dot is 1 on delta, all of that. Now, from the last video, r dot squared was this. So I'll just put that in there from the last video, one just prior to this. All right, now the momentum for vector of a photon is a null vector, so p dot p, that's the magnitude squared of the vector expanded out using the metric, the inverse metric and its covariant components is this object here. So let's write that in. Okay, expanding all that out. All right. Remember, dt d lambda is just t dot. D phi d lambda is phi dot. D d lambda is r dot, and so on. Expanding those out. All right, and then what we end up with, so gtt inverse g contravariant components, two indices up, two t's up the top. Btt is this one. Gt phi is that one. Grr is this. And g phi phi is this, the inverse terms. I showed that in the previous video, I won't repeat them here. Okay, expanding that out, because we're putting in from our results we've obtained on the last two slides, dt d lambda is t dot, put that in there, phi dot in here, t dot in here, r dot in here, squared, and phi dot in here, square it. Putting those in, we get all of this. Okay, now, to expand all this out carefully and accurately, we'll take a couple of slides. And I'm concerned not to introduce any errors. So I went to a software package in order to go from this step down to this one. And we know that all of this equals 0 because the momentum for vector is a null vector. So its magnitude squared is 0, or its magnitude is 0. And what we do when we put this into a software package carefully and evaluate it, we come up with this result here. Now, this is a null vector. The momentum for vector is a null vector. So this p dot p must be 0. All right, so the right-hand side of this equation must equal 0 because momentum for vector is a null vector, so its magnitude must be 0. So if this is 0, that means that we can have minus 1 plus h minus a times c times epsilon equals 0, or we could have h minus a times c times epsilon is 0. Okay, either or both. Now, let's work with the last factor because it's straightforward and it should be immediately recognizable. The last factor tells that a equals h on c epsilon. Okay, just rearrange this to get a by itself. But we recognize this as the impact parameter b, which we've used in the last video. B is h on c times epsilon. So let's insert this parameter into the expressions for our coordinates. Okay, so what we're going to do now is we're going to take ct dot, and then we're going to divide through by c times epsilon. So to both sides divided through by c times epsilon on both sides. So it disappears from there, and we get h over c times epsilon. Now we know that to be the impact parameter b. Remember, b is h on c times epsilon. Okay, and this is ct dot and c epsilon. So that's what we've got there. Next, what we'll do, phi dot. Okay, we're going to divide through by c times epsilon again on both sides. So we get phi dot on c times epsilon, and the c times epsilon disappears from here because divided by itself is 1. Divide the h by c times epsilon, okay, and replace those, this part here, b, with a b, and I'll just expand it out and put a b there as well. R dot squared, remember this, we're going to now divide through by h squared. If we divide through by h squared, I did this in the previous video, but I'll just repeat it here. Dividing both sides by h squared, so divide through there. Okay, I took out the 1 over r squared over here and then divide through by h squared. Same over here, factor 2gm over c squared r cubed out the front. And we've got h minus ac epsilon all over h all squared, because we're dividing through by h squared. This gives us 1 over b squared, as shown in the last video. Remember, b is h over c times epsilon. You take reciprocal, you end up with c squared epsilon squared over h squared. You have 1 over r squared, and here you have a squared, again, c squared on h squared is 1 over b squared. H squared over h squared is 1. Over here, h over h is 1. ac epsilon over h is b over a. All right, and I think that actually should have been a over b. I've made an error there. That should actually be a here over b. I don't know how that slipped through, but it has. It's just the other way around. It won't change the end result, as you'll see shortly anyway. Probably why I missed it. Now, next step will be to set b equal to a. All right, so ct dot and c epsilon is this. Remember that? We're going to set b equal to a. So when I put an a here, this becomes a squared. So we have 2gm a squared over c squared r, but we already have a 2gm a squared over c squared r, so they cancel. And we're left with just a squared plus r squared over delta. And if we then multiply through by c times epsilon, we get ct dot is a squared plus r squared c times epsilon over delta. And for the phi dot on the c epsilon, we had this. We put in the b here. Now we change b to a. This b becomes an a. It goes up there. This b becomes an a. And then we have here 2gm a on c squared r minus 2gm a on c squared r, so they cancel. And we're left with just a over delta. And then multiply both sides by c times epsilon, so the phi dot, that's d phi d lambda, is ac epsilon over delta. C dt d lambda is this object here. Okay. R dot squared over h squared, here we go. As I said here, this won't matter because we're setting b equal to a. 1 over b squared gives us this. And a squared over a squared is 1 minus 1. That cancels. 1 minus 1 on 1. 1 minus, 1. A over a is 1. That all cancels. We're left with 1 over b squared. I should have called it a, but anyway, it doesn't matter. 1 over b squared. And r dot squared is h squared on b squared. That's h squared on h on c epsilon all squared. Simply becomes c squared epsilon squared. Okay, that's r dot. And so r dot becomes plus or minus c times epsilon, where the plus means an outgoing geodesic and minus means an ingoing geodesic. Okay, so ct dot, okay, is the derivative of the coordinate, and it gives us information about the geodesic, because if we anti-differentiate this ct dot, if we anti-differentiate that using this, we should be able to produce an analytic expression which gives us the time component for the 4 vector for the velocity of the particle, or for the position of the photon. Okay, r dot is plus c times epsilon. That can be easily anti-differentiated to produce the coordinate r, and so we can produce then the geodesics, a list of all the geodesics that this particle follows. We won't get purely radial geodesics. That's not possible with the frame dragging and so on. That occurs as we approach, increasingly as we approach the stationary limit surface. Phi dot is d phi d lambda is ac epsilon on delta, but again, that looks a very neat expression which shouldn't be too hard to anti-differentiate to produce the coordinate phi. So we can end up now with, we know that theta dot is 0, so we just expect theta to be a constant. Theta equals pi on 2 because we're in the equatorial plane, so theta equals pi on 2. Phi dot will be some expression once we anti-differentiate this. So phi will be some expression, the antiderivative of this. R will be the antiderivative of this, which is, it's very simple. And ct dot, anti-differentiate that, and we'll produce an expression for t dot. Okay, so that could give us the path, the geodesics that light follows in the equatorial plane of a Kerr black hole. Now, these equations describe the geodesic followed by photons in the equatorial plane of a Kerr black hole. So how light moves in the vicinity of a rotating underground black hole, and they're referred to as principal null geodesics of the equatorial plane. together as they fill the space, they form the principal null congruences of this geometry. All right, now just come back to the form momentum vector. The components of the form momentum vector for a photon or massless particle in the equatorial plane of a curved black hole is given by these: ct dot r dot theta dot phi dot. Bear in mind they may be scaled somewhat. And putting those expressions in, we have this, plus C epsilon for outgoing geodesics, minus C epsilon for ingoing geodesics, 0, if you remember here, 0, and AC epsilon delta, where x dot mu is dx mu d lambda. And now we can use the x dot mu to generate the coordinates x mu of the geodesics, as I was talking about with anti-differentiating, that are followed by the photons in the equatorial plane. Now, all of that will be the subject of the next video. Finding those antiderivatives and plotting them is the subject of the next video. And that's it for this one.